linearity, and you'll see what that means in a moment. And then I need to teach you how to get derivatives on the calculator, and that'll go very fast. And if it doesn't make sense to you, then just come after school and it'll take me 60 seconds to show you. Yes, Daniel?
Yeah, the Casio.
Then you're going to have to come in after school and we'll figure it out together. Because, yeah, I'm not going to teach the Casio, I'm teaching the TI. Yeah, the Casio is different. So, and every time I have to do the Casio, I have to go online and look at the instructions again. It never sticks in my head. But we can do that together, Daniel. It's fine. Just come by after school. Although not today, because today I have to leave right after school. But come by tomorrow after school. We'll work it out. Then we're going to learn several things that maybe last year, and I think every single person in this class has learned this stuff, but last year you may have learned it over the course of several days, but today you'll learn it over the course of several minutes. But don't worry, it's actually really easy. It's really formulaic, you know what I mean? And that is, you're going to learn the power rule, the derivative of a constant times a function, the fact that the sum of the derivatives equals the derivative of the sums, and then the product and quotient rules. And I think I'll just present them to you without proving them to you. I'll prove one or two of them to you tomorrow. Today I just want to present it to you and have you be little trained monkeys and just do them. Okay, the first thing, differentiability implies local linearity. Okay. If I have a function like that, let's say, okay, and I decide, you know what? This is a curvy graph, but what about the neighborhood about that point right there? I mean, the graph is curvy right there, correct? But do you see that if I take a close-up of that point right there, as I have circled, it's going to end up looking like this. And then if I were to take a close-up of this point right there, it would end up looking like this. And then if I took a close-up of that point right there, it would end up looking like that. Do you see that when your graph is differentiable, any point you care to choose, if you take repeated close-ups of that point, you're going to have it looking pretty much like a straight line. And that's what we mean by differentiability implies local linearity. That's not true for a corner point. With a corner point, if I had a graph like this, with a corner point right there, then it doesn't matter how many close-ups I take of that point, I'll never get a straight line, right? I take a close-up of this point, and I'm going to get this. And I take a close-up of that point, and I'm going to get this. And I take a close-up of that point, and I'm going to get this. You see what I mean? Like there's no way to get rid of that fold, that wrinkle. What do you call that? A kink. There's no way to get rid of that kink when it's not differentiable at a point. First of all, do you believe that it's differentiable? You do repeated close-ups and you get a straight line, but if it's not differentiable, like a corner point, or let's say it was a jump discontinuity, okay? Do you believe that as you take repeated close-ups, you can never make that thing go away? Okay, the reason I need you to believe that is because what is going to happen with us is we're going to get incredibly complex functions, but we're only going to care about the values of that function over a small neighborhood. So that, sure, it looks all curvy when you consider all real numbers as the domain, but if you consider some small neighborhood of the function, it looks kind of like a line. And so our goal is going to be to approximate the function with a straight line. We're going to make a linear approximation. That is, someone's going to have some weird function like f of x equals, I don't know, tangent of x minus log natural of x plus e to the x squared minus cosine x. And you're going to take something horrible like that, and you're going to say, yeah, but I only care about that function over this domain. And I can approximate that portion of the curve with f of x equals negative x plus 5. You know what I mean? Well, that's way easier to deal with than that, right? And so we're going to want to make what's called a linear approximation. But the only way you can make a linear approximation of a graph at a certain point is if the graph is differentiable at that point. That is if this phenomenon occurs. Alrighty, so let me just write that there. Since differentiability implies local linearity, that means function must be differentiable at a point. Function must be differentiable at a point in order to make a linear approximation at that. A linear approximation at that point. So, hey, that's it for that. That's all I wanted to say about that. We're not even going to do any linear approximations. That comes later. Okay, next. Derivatives on your graphing calculator. Get out that graphing calculator of yours. Oops, thanks. I don't want to have a fall on you. Is that in focus?
No.
Do you guys don't think that's in focus?
There you go, right there.
Okay, clear, clear, clear. Alrighty, so let's say f of x equals x squared, okay? And I want f prime of 3, okay? Well, you guys know that the derivative of x squared is 2x, so f prime of 3 would be 6, right?
Yes.
But I want to show you our calculator doing it. So here's what you do. You get your calculator and you go math. And then you go down where it says math. If you have a TI-83, you go down until it gets to n deriv. That means numerical derivative. And you press enter. Then you plug in your function, x squared, then comma, okay? And the next thing you have to do is actually tell it what variable you're taking the derivative with respect to. So you put an x next. Now your calculators may work differently or look different. It may actually do this sort of thing, where it goes d and then puts a square there, and then d and puts a square there. Okay, well, here you would put your function x squared, and here you would put the variable x, because you're taking the derivative of x squared with respect to x. But on our calculator, it goes linearly, it goes horizontally. Okay, and then finally you put in the number 3, and I get 6. Is it happening for you guys? What kind? Do you have an N spire, Jessica? Oh, so it's happening for you. Cool. Is it anybody not happening for them?
I had to use a different way, but I got it.
Okay, cool. Yeah, however you can do it is fine. So that's the first way to do it. To get, I was just looking around for quizzical faces, and yours looked quizzical. But that's just the normal way you know, they always look that way. Okay, great. So next, let's say I had a function like here, clear. So put yourself in function mode and put x squared there. And you know, I'm going to do zoom standard. Is that going to get me a parabola looking thing? Okay, or maybe, I don't know, zoom standard is fine, I guess. And let's say I wanted to graph the derivative. I want to graph the derivative. Well, I would do the same thing. I would do math and then go down until I hit n deriv. Okay, and now I want to get the derivative of the function that's in y1. So I could actually just plug in x squared, and that would be easiest. But let's say that function was rather complex. Then I could go variables, y variables, function, and then y1, and it'll actually put y1 there. That way I don't have to retype whatever crazy function I have in y1. Just press VARS, variables. And so I y1, and I'm going to take the derivative with respect to x. But now I want to graph this not just for x equal 3 like we did a moment ago. I want to graph this for all the values of x that I'm going to graph. So you know what I'm going to punch in there instead of 3? X. Okay, so now I'm taking the derivative of what's in y1 with respect to x, and I'm going to plug in all the x values. So I do graph, and now here comes my derivative. And you'll notice the derivative is aligned with the slope 2, which is what you would expect from x squared. You see what I mean?
Yes.
So like, here, I'm going to do another one, clear. Let's say I graphed sine of x. And let me make sure I'm in radians mode. Okay, cool. So I'm graphing y equals the sine of x. I'm going to set my window to be negative 2 pi to 2 pi. And I'm going to have the y go from negative 1 to 1. Okay, so here's my graph of the sine of x. Y equals the sine of x. Now, I'm going to graph the derivative of that. So I go variables, y variables, function y1. Oh, wait, I forgot to do n derivative. Now, go down to 8, n derivative, and then variables, y variables, function y1, and then comma, take the derivative with respect to x, and I'm going to plug in x, because I want all the x values. And so now I graph this guy. Oh, by the way, if I want my graph to look different, I can press enter there. I'm going to make my graph heavy. You ever done that where you go way to the left and you can change how it graphs? Anyway, I want to make it thick. And here we go. So here comes the derivative. That thick graph is the derivative of y equals sine of x. And what is the equation? What does that appear to be, that thick
Cosine
graph?
x?
Yeah, cosine. And so it turns out, yeah, the derivative of the y equals the sine of x is y prime equals the cosine of x.
Is the derivative of cosine sine? A sine term?
I don't know. Let's find out. Here, clear. Let's go ahead and put cosine here.
Well, you could have just left the second one.
Don't, you're confusing me. Right. Okay, here we go. Here comes cosine x. And then here comes the derivative of the cosine of x. The thick line is the derivative of the cosine of x.
Bless you.
So it looks like the sine of x except for one thing. What's true about that guy? I mean, it's going through the origin.
It's the opposite. It's the
negative.
The negative of the, oh, so the derivative of the cosine of x is the negative sine of x. Yeah, that's what it is.
What?
Okay, great. So you guys okay with doing derivatives on your calculator?
Yeah.
If not, then thank you for nodding, Jessica. I felt affirmed just then. I appreciate it. So, but if you didn't get it, or if you have a Casio, which by the way, you know who invented the Casios?
Casio.
The devil. So if you need help on the Casio, I'll help you with that. Like I said, it just means reading the stupid instruction book, because nothing on the Casio is intuitive. Like nothing is the way you would think it should be. So you're just stuck having to read the instruction book. Okay.
But didn't they say that? Oh, never mind.
What's that?
No, don't worry.
Okay, now let's go ahead and do power all of our happy little rules of derivatives. How many people know the power rule? How many people know that at f of x equals x squared, that f prime of x is equal to 2x? How many people know that? Okay, good for you guys. I can give you one as simple as this that you guys are going to get wrong. So it's going to be pretty funny when that happens. I'll just laugh at you guys. I'll do a horse laugh at you guys.
Well, someone's gonna get it right.
Yeah, I'm sure someone will get it right.
And
I know it's you, Adrian.
Just by randomness, someone will get it right.
the randomness.
Or someone who took your class last year.
Wait, what? No, there's no one in here that took my class last year.
Yeah.
You didn't take my class last
I
year.
mean, but it,
In AP Physics he took last year. But not AP.
you had more.
Okay, here we go. So you guys okay that the derivative with respect to x of x to the n power equals n times x to the n minus 1 power? You guys okay with that? And it doesn't matter what that exponent is, you got to stick that exponent out front and take one away from it. So let me ask you this. What's the derivative of 1 over x squared? Well, what would you have me do first?
hold the x squared.
Yeah, you must turn it into something that looks like this. That's your goal. Whenever you apply power rule, you got to turn it into something that looks like this. So we're going to say this is the derivative of x to the negative 2 power. Are you guys okay with that? Now I can take the derivative of x to the negative 2. You tell me, what number should go out front?
Negative 2.
Good. X to the power of what power here?
Negative 3.
Negative 3, not negative 1, negative 3. You got to take 1 off of that. So it's negative 2 times x to the negative 3, or if you prefer, 2 over x to the third. You guys okay with that? Okay, let me give you another one. The derivative with respect to x of the cube root of x. You tell me, how should I rewrite that function before I take the derivative?
X to the 1/3.
X to the 1/3 power, correct? You're taking the derivative with respect to x of x to the 1/3 power. You must write your exponentials as exponentials. Don't have it look crazy like this. It's got to look like this, x to the n. And now, I'd like everyone to please get the derivative of x to the 1/3 power. What is that? Stupid bottle. You know, the bottles get hot and then they expand and now they don't stand up anymore. It's really irritating. How many people got 1/3 x to the negative 2/3 power? Yay, good for you guys. And if you're in Mrs. Loftner's class, if she didn't like negative exponents, then you could actually write it like this, 3x to the cube root of x squared. You could write it like that if you were so inclined. Yes, Jessica?
Can we leave it with the negative exponent?
In Mr. Shana's class, yeah, for the most part, absolutely. Sure. Okay, and now here comes the one you guys are all going to miss. Are you ready for it? Here comes the derivative with respect to x of 1 over the square root of x to the 3rd power. Good luck, you guys. Good luck. No one's going to get this right. I apologize in advance. But don't feel stupid.
Are you sure about that, Mr. Sheen?
The square root of x to the 3rd. By the way, I don't even need that 2 there. I just put that there for you guys. Alrighty. Hey, I'm going to do this now, and we'll see how many of you got it right. Are you okay that 1 over the square root of x to the 3rd is x to the negative 3/2 power? It's negative because it's 1 over it, and it's 3/2 power because it's a square root, so that becomes the denominator of the fraction. It's x to the 3rd, so that's the numerator. Then the derivative is going to be negative 3/2, and I have to subtract 1 from that, so it's negative 5/2. How many people got that answer? Okay, never mind. I guess you'll get it. All right. Any question or problem on that? Alrighty, then next comes a couple of quick rules about constants and adding. And again, these go without proof. The derivative of CU, and by the way, U is the general term we use for a function of x. We're essentially saying we've got some function of x like tangent x plus x to the 4th power or some crazy thing with x's in it, and we'll just call it u for short. The derivative of c times u is equal to c times the derivative of u. That's all. That rule says if you've got a constant, you can just put the constant out front. So let's say I had this, f of x equals 5x squared. What's f prime going to be?
10x.
Yeah, 10x. Just take the 2 and multiply by 5, right? The 5 is of no account. Okay? If you want the derivative of 5x squared, what this is just 5 times the derivative of x squared. You see what I mean? You just ignore the 5. The 5 just, you can multiply the 5 on at the very end. You see? And then the derivative of x squared is equal to 2x, and then you get your 10x. That's something that, again, for many of you might be just habit by now. It just makes so much sense that you never really needed someone to explain it to you, but that's not the way I teach the course. I need to explain everything you guys learn. So you guys okay with that? Okay, then the next thing is the derivative of the sums is equal to the sum of the derivatives. That is the next rule is if you have the derivative of u plus v, this is equal to the derivative of u plus the derivative of v. The derivative of the sum is the sum of the derivatives. So let me give you guys one to do. Let's say I had f of x equals 4. Oh, I know what I'm going to do. Yeah. 1 over the square root of 2x plus 3x to the third. I'd like everyone to please find me the derivative right now. I'll give you 30 seconds. This is one no one's going to get, and I'll feel really smart about it. Camera's looking good. I haven't looked at it yet. I mean, my experience with that camera is things tend to be blurry. And so like right now I'm blurry.
No, you're really clear.
Well, there I'm clear, but what's actually being recorded on the retina of that stupid camera is blurry. Like I must have dropped the camera one too many times, so now the lens is off kilter and I don't know how to fix it without destroying it. But it'll be good enough. I mean, even if it's blurry, you'll still be able to read the board. So you guys will just, if anyone needs to see these, they'll see blurry videos.
And then Mr. Sheena smiling.
I'm trying to smile more because you got to let a smile be your umbrella. Okay, here we go. Here comes the trick. You know what? You know what you do with something like this? This is just another example of this. Are you okay that 1 over radical 2x is the same as 1 over radical 2 times 1 over radical x? I urge you to use that strategy. Any other strategy you used is going to blow up in your face. Just take that radical 2 out. Treat it as a constant. You see what I mean? So now when you take the derivative, all I'm doing, oh, by the way, I'm going to rewrite this now. This is 1 over radical 2 times x to the negative 1/2 power plus 3x to the third. Are you okay that 1 over rad x is x to the negative 1/2 power? And so now I'm going to take the derivative, and this 1 over rad 2, hey, it's just a constant. I don't have to do anything to 1 over rad 2. It's no different than 5 or 12, you know? So the derivative ends up being 1 over rad 2 times negative 1/2 times x to the negative 3/2, and then plus 9x squared. You see? And so this answer ends up being negative 1 over 2 rad 2 times x to the negative 3/2. So I could put it in the denominator if I was so inclined. Did anyone get an answer that looks like this? Yeah, I guess this was the problem no one was going to get. Yeah, Andrew.
No, I got it.
You got that?
Yeah.
I don't believe you. You're lying. You're like Donald Trump.
You want to see it? I did it.
No. Okay, I'll believe you. Yeah, I'll believe you. And the Mexicans will pay for it too. I totally believe you. Okay, great.
Wait,
No.
I have a question. Is it okay if I put the x cubed on next, so the radical 2x cubed, but I did the x cubed in parentheses?
Oh, so you did this? Wait, negative 1 over 2, and then 2x to the third power, you did that?
And then, yeah, in parentheses, the x
Well,
cubed is in parentheses.
Okay, you don't need the x cubed in
Yeah.
parentheses. Yeah, that's a correct answer.
Okay. yeah,
Sure, so you
definitely
did it
get-
right. Cool. Wow. But anyway, that's my recommendation. If they put a number next to your x, just pull that number out as a constant. You just save yourself a lot of heartache, you know, instead of doing, because you could also do this doing something called the general power rule, which we're gonna learn tomorrow. But, I mean, why use general power rule when you can just do that and save yourself all the headache? Alrighty, well, hey, now it's time to do product and quotient rules. And I'm not gonna prove them, I'm just gonna show them. I'll probably prove them tomorrow.
Oh, I forgot about it.
Product rule.
Dude, I've never subtracted, I forget.
The derivative with respect to x of u times v. Remember, u is just some function of x, and v is a function of x. You would think that it would be u prime times v prime. You'd think that it'd be the derivative of u times the derivative of v, but no, it's not that at all. It ends up being the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. Do you remember doing that?
Yes.
Yeah.
Well, if you didn't, that's fine. That's what you're gonna do. The derivative of the first times the second plus the first times the derivative of the second. That's the product rule. That's how you get the derivative of the product of two quantities. Let me give you an example. Let's say I wanted the derivative with respect to x of x squared plus x plus 5 times x to the third minus 3x squared plus 2x plus 3, okay? I want the derivative of that product. Well, I don't want to do FOIL or FOIL, you know, I don't know, that's a lot of hassle. I'd rather do the product rule. And so this is going to be the derivative of the first guy, 2x plus 1. Are you okay that the derivative of 5 is 0?
Yeah.
Why is the derivative of a constant 0?
That's it, that's what it is.
Yeah, because it has no variable, or the exponent of the variable is 0. If I want the derivative with respect to x of 5 times x to the 0 power, which is what 5 is, this is going to end up being 0 times 5 to the x to the whatever. And by that time, who cares? I mean, I got 0 times that, and that's going to be 0. Another reason is, remember, the derivative gets you the slope of the tangent. So if I've got this line, y equals 5, f of x equals 5, what's the slope of the tangent for every point on this line?
0.
0, right? It's a horizontal line. So I hope it makes sense to you why the derivative of a constant is always going to be 0. So that's why I just get 2x, and then the derivative of the first times the second plus the first guy, x squared plus x plus 5, times the derivative of this guy, which is 3x squared minus 6x plus 2. And at this point, usually I just let you just keep it like that. I'm not going to have you multiply it out and simplify. That's good enough.
Are you serious?
Really?
Yeah, yeah, absolutely. Why multiply it out? I mean,
I am Mr. Walker.
I need to go have a
okay,
talk
so you
with
guys
Bob.
ready to do it on your own? Please get me the derivative of x squared minus 5 times x to the third plus 6. Please get me that derivative using product rule. Please do it now.
I think you need to have a talk with Ms. Lofgren about that.
No, I mean, I think it was important that she did what she did, but we're going to be dealing with functions that are just so incredibly complex that I don't want you to waste your time multiplying it out. Whereas she dealt with functions that weren't that complex, so it was okay for her to have you guys multiply it.
It was okay for her to waste our time.
Hmm?
So it was okay for her to waste our time.
It's not a waste, I mean, it wasn't that much time. You little whiners, you little belly achers.
I probably spent a full day in total last year.
Like 24 man hours,
Yeah.
just doing algebra, just simplifying.
That's right.
Well, it's time well spent. I mean, you could have been doing drugs, but instead you were doing this.
Or I could hang out with my family.
Well, that's right, you could have been giving love and receiving love from your family. Well, when you put it that way, sorry. Okay, you guys done?
Yes, sir.
Okay, hey, derivative of the first
Oh.
times the second plus the first times the derivative of the second. How many, oh wait, just 1 second. Okay, how many people got that answer? Yeah, that's it, that's the product rule. Just derivative first times the second plus the first times the derivative of the second. That's all you gotta know, okay? Okay. Next comes quotient rule, but unfortunately I don't have enough time to do it, so I need to take some problems off of your assignment. Because we're done, baby. Okay, just 1 second.